Hi, good evening, friends, and welcome to the revision session for ADS for the end term quiz. And this is part two. Part one we had last week, and this is part two. Thanks for joining in. So, straight away, I will just share my screen and let's start. The format will remain the same, it will be kind of a discussion. So, anywhere you feel stuck or you have got a query, please pipe up and we'll discuss out that issue. I hope my screen is visible. If somebody can gives me a hands up.
Not visible, sir.
Okay, but to me it is looking visible. Surpi, is it visible to you? Hello, Ravina.
It's not visible to me yet.
Okay, okay. So I will share again. Okay, just tell me when it becomes visible. I think there is some problem in my bandwidth today.
Yeah, it's visible now.
Okay, thank you. Thank you so much. Yeah. Okay. Okay. Yeah, so during our last revision session, we had covered week 7 and week 8. So before moving forward, we will just revise that also, and then we'll go to week 9 and week 10. So we had covered generalization error in total with the finite number of classes in the hypothesis class and the finite also. And we had solved the GAs also. Okay. So before we move forward, I would like to correct something which I had incorrectly mentioned in the last session. These notes I will share after. Okay. So I had made okay, one error last time. So when h is finite, h is less than infinity, then probability of error of model trained on your training class and error on this is basically test data set is greater than epsilon is less than equal to it had come 2 to power n. In my last lecture, I had incorrectly mentioned n to power 2 and e to power minus 2n epsilon square. Is that okay? And when h is finite, then this becomes less than equal to
So it should be 2 to the power n plus 1, I think.
it is 2 to okay because here 2 comes. Yeah,
Yes.
yeah, yeah. Because that in Hofferding's it is 2 here and h is finite and for interval class it will become n to power 2 to e to power minus 2 and epsilon square. Is this okay? And when h is infinity, then what is the value here? Again, it is 2 to power n, or it is here it becomes 2 to power.
Sir, n to the power d, I think it was
Yes,
somewhere mentioned.
yes, n to power d, where n is the number of class.
And d is BC dimension.
D is DC dimension. Yes, BCD. So this part and this part I had incorrectly interchanged. So that I wanted to correct before we start. Okay. So this time we will slightly go faster because we have to complete week 9, 10, and 11. So now we come to week 9 and week 10. So here I have covered this increasing, decreasing. So this is part is okay. VC dimension, everything is clear. Does anybody need explanation for VC dimension? Ravina?
Yes, sir, it's clear, sir.
Yeah, okay. So we will not spend time. VC dimension, remember these steps, only that. And so there are two players, player one and two. Player one, basically, he gives the points, or we get points. And if the player one is not able to give that edge which correctly classifies them, then the previous n which is there, it becomes your VCDIM. Simple. And I will not cover that compression also, because compression ratio size is equivalent to VCDIM. So directly apply your VCDIM concept and you can find that. Okay, and here this will become 2 here, like Ravina had mentioned. This becomes 2n to power d e to power minus 2n epsilon square. So estimation error we will come. So we have finished with the generalization error. Estimation error is basically error of, or this is test error minus d, the best hypothesis class which we get from the entire thing, h. Now we can break down this in LDHS, and on training data set, the best model which we get, which is known as HSERM, we subtract it, we add it, and we then LDH. So this HSERM is the best model which we get in the training, which gives the best training accuracy. Now further what we can do, this HSERM which is there, we also can add as H star. H star is basically, this is the best model which is from hypothesis class. So this is the training error of that. This is the, we add and subtract, and then we find out, see this middle part which is there, this is the best model we have got from training error, and this is the other model which has come best model from the hypothesis class. So when we have got the best model and this is the another model, so this value will always be negative, because this error will always be less than this error. So we can discard this. So then it becomes that it will always be less than equal to this term and this term. And then when we take absolute values, we can say that this value will be less than equal to 2 maximum of RSH star and LDH. And this we have calculated, this we can calculate, we had done during the generalization error. So this we can break down that it will be less than equal to probability of max RSH star minus LD. This 2 comes here, epsilon oblique 2. We put in the Hofstad's formula, and then it becomes ND. Here also 2 will come, 2ND e to power minus 2n, and here become epsilon oblique 2 whole square. Now this finding ERM is NP hard. So for this, what we do, we select loss functions. So we select loss functions like logistic loss or hinge loss. So this is all about your estimation loss. Estimation loss. So estimation loss also we have broken down that this will always be less than equal to this point. So here point to note is that as n goes to infinity, this probability of this error also goes to 0. So this n is very, very important. And from here we come to the last term, which is the approximation loss, which is the best model LDH minus R star. And what professor he covered, that for solving this theoretically, what we do, we select many hypothesis classes. And for those hypothesis classes, then we do ERM for everyone. But even ERM is NP hard. So this is a theoretical concept. So we cannot implement that. And from there, the thing comes which is there, the regularization. So when we do the regularization is nothing that what we are doing in the regularization, we are decreasing the bias, because this error, approximation error, is also known as bias error. So we add the regularization factor due to which this approximation error becomes less. So this was for week 10. And this GS we had solved okay last time. Surupi, Ravina.
No, sir, this one I don't think.
Okay. So this is week 10, week 10 one. So this we had a discussion on WhatsApp. Is this first question is clear, or do I explain it again?
Yes, sir, it's clear.
Okay. So this is very, so here only what I will cover. There is a question on the in the PYQ also. So if you have got an interval class, for example, if you have got a single interval class AB, HAB, then what will be the VCDIM?
2.
Very nice. And if we have got, for example, AB union CD, then
4.
yes. So please remember this. Okay. So there might be a question on this. Okay. Then now consider the class hypothesis edge of decision trees over R2. Given n distinct points in R2, how many possible labelings are possible with classifiers drawn from H? So remember, if we have got, for example, a decision tree, we know the number of classes is what? This is equal to your basically number of leaf node nodes which are possible, and the number of possible leaf nodes is 2 to power n. They can duplicate, but we are asking the max number of labelings. So in a DT, the max number of leaf nodes is 2 to power n. So here, that is the answer for this. The second question is this only, which we just discussed, two interval classes, AB union CD. Then you can check that all combinations you can do for n is equal to 1, 2, 3, 4, you can do. But as you increase n is equal to 5 and you select 1, 0, 1, 0, 1, then you cannot do. This one interval class, this second interval class, this gets shattered. So you cannot shatter this. So you go to last one. That's why VCDIM is 4. Then we come to VC dimension of hypothesis class HWB, where HWB is WTX. So remember here, bias is also there. So for this, for a linear operator with bias, D is equal to this, R is equal to 2 plus bias. So this is important. That's why this D becomes 4. So here in this question, if it becomes W is equal to R4, then what will be the VCDIM? Nitish?
Because of bias.
Yeah, 4 plus 1 is equal to 5.
5.
Yeah.
Yes, sir. Yes, sir.
Okay. Next one, H is a hypothetical class with finite VC dimension. So this is important. S is some data set with endpoints, and HS belongs to H is a classifier trained on S. Which of the following are true? So this is for a finite. So the train error of HS will be very low. It is not necessary because we have taken some HS, we don't know. The test error of HS will be very low. It is not necessary. If n is large enough, then the train error and test error will be close to each other with high probability. So remember, we had discussed during the last session also that this probability of HS error as HS minus LD HS greater than equal to epsilon less than equal to 2 to power H e to power minus 2n epsilon square. This is applicable for all the models. It is not that you take out the best model only. It will be applicable to all the models. And if we increase the n, then this error will reduce. So this third point is valid. Next is consider a data set for a binary classification problem with the feature in R2. Each entry has got x1, x2, y, where y is either 1 or minus 1 is the label, and x1, x2 belongs to R2. These are the points which are there. Consider the hypothesis class H is equal to HW, W belongs to R2, and the norm of W is equal to 1, where HWX is equal to 1, WTX greater than equal to 0 or minus 1. So if we plot these points, these are 0, 0, these are the positive points, these, and these are the negative points. So we can have W norm is equal to 1. So let W is equal to AB. Therefore, A square plus B square is equal to 1. This is the first point. Now, point 1, 2, 3, which are there, they are positive. So the point, this 1, AB doesn't matter because it is on 0, 0. So for point 2, if you take minus A plus B is greater than equal to 0. For point 3, A minus B is greater than equal to 0. So it means A is equal to B, and as A square plus B square is equal to 1, 2A square is equal becomes 1, A is equal to 1 by root 2, and then we get B is also 1 by root 2, and A plus B is equal to root 2. Is this clear, or do I have to explain this question?
Could you explain the AB part again?
Okay. Yeah. Okay. So Surpi here, okay, they have given W is norm is equal to 1. So we take W, for example, is AB. Okay. And therefore, A square plus B square is equal to 1.
Yes.
Okay. Now for point 1, this will become AB into 0, 0. This becomes 0 greater than equal to theta. So from here, we are not getting any information, no info about AB. Okay. Now we come to point 2. Here AB point 2 is what? Point 2 is minus 1, 1. So this will become minus A plus B should be greater than equal to 0. From here, this is number 1. And from point 3, we get AB into 1 minus 1. That is A minus B is greater than equal to 0. This is 2. Now, if you comparing 1 and 2, it becomes A is equal to B. Is that okay? It gives
Yes.
B is greater than A, and here it is A is greater than B. So from this, A is equal to B. Now you put this now, A square plus A square is equal to 1. Therefore, 2A square is equal to 1, A square is equal to 1 by 2, A is equal to 1 by root 2, multiply by root 2, root 2. So this becomes root 2 by 2, and B also becomes root 2 by 2. Therefore, in the question they have given, asking A plus B. This will come root 2 by 2 plus root 2 by 2 is equal to root 2 is equal to 1.41. Okay. Clear, Surabhi?
Yes. Yeah,
Okay.
yeah.
Okay. Now we come to next question on the same. So now they're asking find the train error of the ERM. So see, now we have selected compute ERS HSERM. So HSERM can be, see, these are the white points. So HSERM can be either 1, 1 or it can be minus 1, 1. So either it can be like this or it can be like this. Then only we will get the best results. And in both cases, if we see, there will be one misclassification. If we take this, then all these points will be positive and this will be incorrect. And if we take this, misclassification. So train error is equal to 1 by 5. Is this okay, Surupi?
We are classifying based on the line going through, like
Uh,
y is equal to minus x.
Yes,
that
yes.
slope.
So see, if we have got, for example, we have got these points. We have got this one positive point, second positive point, third positive points. And we have got one red point here, and we have got red here. Now, what will be the best classifier? ERM. And it is WTX greater than equal to 0. So if we have got WT like this, then this becomes the decision boundary. And all these points here, they will be positive. This is the best ERM.
Yes.
Okay. Now, and this will be negative. So this is correct. But this here, error is how much? 1 by 5 is equal to
Oh,
0.2. Okay.
yes, yes.
Okay. Okay. Now we come to next question. So consider the following labelings realized by some classifier. It is very, very easy. Just you take it and just see whether both the classes they are getting distinguished or not. So if we check, for example, ABGF, so if we make A, B, here G, and we are taking F, now see here, it includes red also, it includes green also, so it is not distinguishing. Similarly, IHDC, IHDC here, this is the IHDC, oh sorry, IHDC. This is I. This is IHTC, small one. So see here, one green point is outside. That's why it is not there. When we take CEID, CEID is from here. We start from here. C, we go to I, then we go to C. E is also there. So where is E? E is here. We come here, and then D. So see here, all the green points are inside, red points are outside. So that is the perfect classifier. So compression scheme output. This we have done. Now we come to triangle question. This was slightly evolving question. So here it was like that. How to basically, what is the
Analogy, your screen is freezing up sometimes.
yeah, maybe there is some bandwidth issue. It is okay now.
It is visible, but sometimes, like if you're writing something, it
Yeah.
takes some time to come
Yes.
back.
Yes. Yeah. Due to the motion. So for this triangle question which is there, we have to basically denote this triangle. So make this triangle. See, this is a right angle triangle. So this is above x. So by just by this x, we can denote this side. This point which is there, or this is y, for example, above y, and this is more than x, we can denote this two sides. For the slant which is there, we need 2 points. So we get one VC for VCDIM. So we get 1 plus 1 plus 2 from here. So this becomes 4 compression ratio.
So if it is not in right angle triangle like other triangle,
Yeah,
then there will be two slants. So is VC dimension increase or remain same?
it will increase, okay, Ravina, because then you will need, okay, for this also, for this also, and for this also.
So is it 5 or 6?
It will become 6, okay.
Okay, yeah.
Okay. Now, next question will come. Suppose this is a Pn parameterized by n, denotes a set of all polynomials of degree odd plus n. Note there is a one-to-one correspondence. We define a hypothesis class. So see here is the hypothesis class. Hx is equal to px plus norm of px divided by 2 norm of px. So see here how every hx will look after, will look like. So this is px, this is the norm, so it is a scalar divided by scalar. So your VC dim which will be there, basically it will be the VC dim of px. Now we know that px which is there and Rn plus 1. So px dim which is there for H2. So VC dim will be n plus 1 if it is in n dimension in this case, because there is a bias. So find the VC dimension of H2. So H2 VC dimension is
2
2,
plus 1.
1 is equal to 3. Okay. And now for H5, they are asking what is the required sample size and to have 95% confidence that your generalization error is at most 0.05. So here we have to use our formula of n. So here generalization error is at most 0.05, 95% is confidence. It means your delta which is there, it becomes 0.05. This is 95% confidence. Epsilon becomes 0.05. And we know that probability of your generalization error more than epsilon less than delta is approximate. Here it will become 2.
Sir, I am not able to solve it after this equation.
Yeah. So here we cannot do here manually. We have to do hit and trial. So what I did, I wrote a Python code for this, because see this one part which is there, you cannot solve this manually.
Yes, sir.
Either what you can do, you can try n, for example, you can try n is equal to 1000, then n is equal to 5000, 10,000, 15,000, and then you start zeroing down. But then it will be a lot of time consuming. So it can be done only by writing a code for this. Okay. And remember, Ravina, I would like to mention here that in the GA, they have not considered this too.
Yes,
Okay.
sir. Yes.
Okay. Yeah. Now, this is an important question which has been repeated in PYQ also. Please remember this. If the hypothesis class is, for example, there are 64 models, find the tightest upper bound for the VC dimension of H. So here always remember that if there are two classes only, for example, there are two classes, then 2 to power d will be less than equal to number of hypothesis classes. So 2 to power d, it becomes 64. So 2 to power d becomes less than 2 to power 6, or d is less than equal to 6. Now here in the PYQ, what they have done, they have made it H100. So in that case also for H100, it will remain the same. So 2 to power d is less than equal to 100. So for 100, what we can do, we can take 2 to power 7, which becomes 128, and we take 2 to power 6, which is 64. So if we take d is equal to 7, then this is not valid. So for to become valid, d will become equal to 6. Is that okay?
Yes, sir.
Okay. Okay. Now week 11, I will just cover the theoretical part and the important things to note, and what are the, so I'll cover from here. And basically the intuition part. So week 11 basically starts with privacy, that if you are carrying out a survey and you have got some responses x2, x3 up to xn are there, and they just tell you 0 or 1. For example, you are asking whether you have voted or not. And so the people, if they give the full information correctly, then what will happen? For example, I have got this honest information, then the utility is very high, but the privacy from this data, anybody can find out that who has voted and who has not voted. So privacy is very less. Now, this is for this. But if everybody lies, then what happen? The privacy is high, but your utility is low. So this is the first thing. Now, with that, if we start, for example, random response means that I will respond correctly with a probability. And what is that probability? That y is equal to xi, that is correct. I'm giving correct response. And the probability of this p is equal to xi is given by e to power epsilon divided by 1 plus e to power epsilon. Therefore, p y is not equal to xi will become 1 minus this e to power epsilon, 1 plus e to power epsilon, which becomes 1 over 1 to power e to power epsilon. So when we take a survey, every person, he answers with this probability. Now, when we connect this, for example, now again we have got all these responses, but all these are responses which are random. So now I make a term expected of, so these are, I have got y's here, y1, y2, y3, and yn. So what I do, I find a zi is equal to yi minus 1 over 1 plus e to power epsilon into 1 plus e to power epsilon over e to power epsilon minus 1. And now what I do, I find the expected of z. Now remember, before coming to expected of z, from here this probability of y's, expected value of y will become xi into e to power epsilon over 1 plus e to power epsilon plus 1 minus xi into 1 over 1 plus e to power epsilon. Now, if we do this, we can write it as, we can take xi, this will become e to power epsilon minus 1 over 1 plus e to power epsilon, and next term will become e to power epsilon over 1 plus e to power epsilon. Sorry. This is your expected of y. This is okay? This one? Ravina?
Yes, sir.
Okay. Now we had defined z is equal to yi minus 1 over 1 plus e to power epsilon into 1 plus e to power epsilon minus 1. Therefore, expected of z will become expected of this. And if we open this, this will become expected yi into 1 plus epsilon, this 1 e to power epsilon minus 1 into minus, when you multiply this will become 1 minus e to power epsilon minus 1. This is okay. Now here these are fixed terms, only random is yi. So this will become 1 plus e to power epsilon over e to power epsilon minus 1 expected of y minus 1 over e to power epsilon minus 1. Now if you put this term here, whatever we got this expectation of y, then expectation of zi will become xi. It means if I have taken responses, and from that responses, what I have done, I have found the value of zi. This is nothing but I got the response, and these are the values which depend on the epsilon. And then when I take the expected value of zi, then it is equal to xi. So by this, what is happening, see here, that I am able to maintain the privacy. So how do I maintain the privacy? That random response and your y is equal to, for example, xi, which is there, xi prime, which is, sorry, xi is there. This will be e to power epsilon random response y is equal to xi prime, and it is less than equal to, and it is greater than equal to e to power minus epsilon y is equal to xi prime. So this epsilon factor which is there, if it becomes 0, then they both are same. If epsilon is equal to 0, then there is total privacy, because nobody can distinguish. So there are two responses. One is x1, x2, xn, which is here, and another set is x1 prime, x2 prime, and xn prime. Now in this sets, only one value is differing. Rest all are same. Only one value remains the different. So when we make epsilon is equal to 0, then these two data sets or responses, they look similar, and there is total privacy, but there will not be any utility. Utility will be very low. So this I have explained. Probability, you can see this x prime and all that. This I have done. Privacy.
So I have a doubt here in the Z part.
Yeah.
So like first we are taking y, and y is the expected value of x. Not exactly like it's like we derive it by expectation multiply with probability.
Huh.
So after that we take z, which was de-biasing and descaling y.
Yeah. Just hold on. Just hold on. Just give me a minute. Huh? Yes, Ravina.
So, sir, we are adding some bias and then we are debiasing it. So, what's the point? I didn't get it.
Okay. Okay. So remember this y which is there. It is not a bias. Y is a probability. Probability that y is equal to xi means he's
So,
giving
sir,
an,
like after doing that multiplication, we the equation which we get,
yeah.
that is having an bias and in scale.
No, 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 no. So I will come to the scale later part. Now you're confusing with the trusted curator.
I
Okay.
think.
Yeah. So Py is equal to Xi is equal to P, make it a probabilistic that he will give the correct answer with this probability. For example, he wanted to say, yes, I have voted, and he says, I have voted by this probability. And probability of incorrect or honest is equal to 1 over 1 plus. Is this okay?
Yes, sir.
Okay. Now then we say that what is the expectation of y? He can either say, he can either give honest reply or he cannot give uh, dishonest reply. So what is the expected value of y? This will become is equal to xi, what was his correct, into e to power epsilon over 1 plus e to power epsilon, plus this is 1 minus xi, because if it's honest was 1, then this becomes 0, or this was 0, then it becomes 1. So this is 1 minus xi into 1 plus e to power epsilon. This we can write down xi e to power epsilon minus 1 over e to power epsilon plus 1 plus 1 over 1 plus e to power epsilon. So this is not a bias, this is our expected value. Okay.
Okay, sir.
And now from here to derive, what you do now, for example, now you have got two data sets, x1, x2 over xn, and you have got another one, x1 prime, x2 prime, xn prime. See, we want to maintain the privacy of this xn who's there. Now, in this case, here he has given some answer, and here he has given different answer. Here he might have been honest, here he's not honest, or here he was dishonest, here he was honest. So we want to find the proportion of this to maintain the this. So when we say this probability of y1 is equal to x1, y2 is equal to x2, yn is equal to xn, we can write down that product of yi is equal to yi minus n minus 1 and xi n minus 1 into probability of yn is equal to xn. This we can write down. Similarly, for the second data set, yi is equal to x1 prime up to yn prime is equal to xn prime can be written as yi n minus 1 is equal to xi n minus 1 x prime into probability y n equal to xn prime. And when you divide this, these all points were same, so they cancel out, and pyn is equal to xn divided by pyn is equal to xn. And now here you put this formula, e to power epsilon over 1 plus e to power epsilon over divided by 1 over 1 plus e to power epsilon. So from here we get this formula which I had just mentioned now, that your random response, probability of random response, where your yi is equal to xn, which is correct, it will be less than equal to e to power epsilon into probability of random response, where yi is equal to x from n, and here comes e to power minus epsilon. Probability of random response yi is equal to xn response. The main takeaway which is there from this formula is that as your e becomes 0, then both these responses which are there, they become identical. It means there is total privacy. You cannot distinguish. But as you increase this e, then they start becoming distinguishable and privacy decreases. Okay. So this is the relation between your privacy and epsilon. Is that okay?
Yes, sir.
Okay. So this was privacy. Now we come to utility. For utility, what we did, we found another thing, zi. We described yi minus 1 over e to power epsilon plus 1, e to power epsilon plus 1 over e to power epsilon minus 1. So this is your scaling which you were mentioning. This is your scaling and this is your unbiasing. Is this correct?
Yes, sir.
Yeah. So why we are doing? Because we want to estimate. So see, utility is what? If I get responses, so from those responses, without knowing whether somebody has given honest answer or dishonest answer, I should come to know about some percentage that, okay, some 40% have given correct answers. That is a utility basically. So when I do the expectation of this zi, this comes to xi. That whatever they said, xi is what? Xi is the correct answer. So it means when I take from the responses, then I will get a fair idea of the correct answers, whether they have given correct answers or not. But I am getting this expected value which is there, which is equal to xi. Is that okay? Explanation?
Yes, sir.
Okay. Now remember, this zi which is there, it has got a scaling of e to power epsilon plus 1 over e to power epsilon minus 1. So when epsilon becomes very, very less, then this value which is there, e to power epsilon minus 1, then e to power epsilon reaches 1 plus epsilon. Okay. When e becomes very, very less, then e to power epsilon which is there, it becomes 1 plus e, epsilon. Is that okay? And this over numerator, it becomes 2, because here it becomes less, so it will come 2, and here you do e to power epsilon minus 1, so this becomes 2 to 2 over epsilon. What does it mean? This means your standard deviation which is there of this scaling e to power epsilon plus 1 over e to power epsilon minus 1 is 1 over epsilon. Is that okay?
Yes, sir.
Okay. And then we know what is the value of uh, what do we say that? Just hold on.
Sir, it is covering the randomized. Are you covering the curator part also?
Now, yes, curator will come after this. Okay, I will just covering this part expected of Zi. So here we have come. So here where we have come, expected of Zi is become Xi. Similarly, expected of Z bar will become X bar. And I was just trying to explain that from where this e to power this epsilon root and from where it has come, because professor directly mentioned this. So see, when standard deviation of Zi is 1 over epsilon, and from the law of large language numbers, error of average is equal to standard deviation over root n. So when we place this standard deviation, we got 1 by epsilon. So this is error of average becomes 1 over epsilon root n. Is this okay? I will just go.
Sir, I want to ask the relation between utility and n.
Yes, yes.
Epsilon and
We are coming to that only. We are coming to that only. Just give me 2 minutes, Hana? I was just coming there only. Yeah. So we were here. So this is your standard deviation. Now, law of large number says that error is equal to epsilon over root n. So here, this error, because this is of for Z, so for Z, error will become here, this is like this will become epsilon of root n. Therefore, what we can say that your 1 by n Zi or Xi, you can write 1 by n Zi, this is of order of 1 over epsilon root n. Now we'll come to Ravina, your question. Now what happens? Your aim is what? Your aim is to make it less. This should be less
yes, sir.
for good utility. So what you have to do? You have to increase n.
Yes, sir. Yes, sir.
Okay. So here, when you increase n, so for a specific epsilon, which governs you get from privacy. Now select n for utility. Is this okay? Nitish, is it okay? Am I audible?
Yes, sir. Yes, sir. Okay.
Okay, so this concept has become clear. So see, in privacy, only epsilon plays a part. In utility, both epsilon and n plays the part. So if we want to have good utility, then your n has to increase, because for good utility, this error which is there, this error term which is there, it has to be less for good utility. So you increase n, this will decrease, and that's why you will have good utility. This is your RR. Any
Sir,
question? Yeah.
sir, if we increase the deviation, then it should imply that uh, utility is also increased.
No, 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 no. See, what is the meaning of utility? Okay, just
Accuracy. So
no, no, no. See, I want to get a estimate of xi. I want to get a xi. Xi is the correct one. Correct answer.
yes, sir.
And how I am getting this xi? I am getting from zi,
Yes, sir.
expected of zi. Basically, I want to know xi, and xi is from zi. So this utility which is there, 1 by n xi minus 1 by n zi, this error for good utility, it should be less.
Yes, sir. Got it, sir.
Okay. And this is order of 1 by root n e. Okay.
Yes, sir.
Okay. Good. Okay. Very nice. Shall we go now to the trusted curator? Any question in order random response? So random response, again, I'll explain what has happened. We have got replies x1, x2, ye the, xn. Everybody has replied y2, yn with a probability of e to power epsilon 1 plus e to power epsilon. So what do? We collect this. For step 1, we find zi is equal to yi minus 1 over e to power epsilon plus 1, and this is unbiasing, and then we do scaling e to power epsilon plus 1 over e to power epsilon minus 1. And when we do this zi, then we find that xi which is there, it is nothing, it is the expectation of zi. So from here, whatever the figures we get, for example, here we get 0, 1, 0, 0, 0, 1, we get, and then we put this. So whatever the expected value of this zi which will come, this will give me the xi. For example, if I get, for example, 40.2, so I will say that 40.2 percentage people, they have given correct responses. And I maintain the privacy also. So that privacy is maintained by the formula that RR, probability of RR, y is equal to x is less than equal to e to power epsilon probability of RR, y is equal to x prime. X prime means the incorrect answer, and this is equal to e to power minus epsilon probability of RR, y is equal to x prime. So from here, this part is covering the privacy, this part is covering the utility, and third part is the relation between utility and n. So that is 1 over n xi minus 1 by n zi is equal to o 1 by root n epsilon. And this we get from where? We get from this formula, from the scaling. We find the standard deviation of this scaling, and then we find the error average. So that was the part for random response. Now, shall we move to the trusted curator? So trusted curator, I will just flash something before we cover. In the trusted curator, what is happening? That we trust the curator. That whatever we will answer correctly. But we know that our curator who's there, when he will release the results, he will release the average. He will not release the average, correct average. He will add some Laplacian noise in that. And by adding that Laplacian noise, nobody can make out or predict what an individual member has answered. Is that understood? What we are trying to do?
Yes, sir.
Yes, sir.
Okay. So this is random, this is trusted. So what do we do? So again, the thing is same. So we have got two parallel, or we can say two neighbor data sets. In one, everybody has answered correctly except the last one. So this is the probability mx is equal to b. This is some function. This is less than equal to e to power epsilon. This is similar to a random response only. Mx is the output of that mechanism. For example, reporting the average. X and X prime which are there, they are the neighboring data set differing by only 1%. That's why it is known as differential policy. Epsilon is the privacy budget. Now, what do? We make a function fx, and in that one is correct fx, which is the correct fx, and second is the another one, we change the nth person. So similarly, like random person up to n minus 1, they are same. So this will cancel out this, and this will become 1 by n x n minus x prime n. Now we know xn minus x prime m absolute value can be 1 only. So this fx minus fx prime, this becomes 1 by n. And this is known as sensitivity. Okay. Now what do? We take the average and we add a Laplacian noise. This is the Laplacian noise. And this is, how does it look like? This is, we write Laplacian of 0 sensitivity over epsilon. So this can become L0. This will become NE. So here what we have to remember, we have not been taught in the course that for a Laplacian distribution, for example, your expected value of x which is there, this becomes this part which is there, the second part of the Laplacian AB, x is equal to Laplacian AB, then expected of x is equal to b. This is a very important property of Laplacian. So here expected of x which is there, this will become 1 by NE. So see, this noise which is there, this is the error. So when you compare fx, f dash x minus fx, this is the error, which is the utility. This becomes of the order of 1 by NE. So what we have achieved here, that earlier in the random response, we had to increase many folds n, because it was getting by root n. But here it is n. So just by increasing some more, we can increase the utility. I hope this is clear, this understanding. This is the only part of the trusted curator. Shall I explain again?
Could you explain in simple language?
Okay. So देखो होता क्या है, चलो मैं बताता हूँ. Okay, just hold on.
I understand the part of the curator is getting true and adding some noise.
हाँ,
But
देखो क्या हुआ,
some
I'll tell you.
mathematics,
No, see, x1, x2, all xn, they gave correct answer. Okay, answer. So
yes.
we have got y1, y2, oblique yn. We have got correct answers. We have given to curator. Now, if curator releases, if he releases correct average, for example, from here, he comes to know, for example, count of y is around 40%, and he releases 40%. Then what can happen if there is a neighboring data set or a data set, then somebody can make out that this person who's there, y1, or this x1 who was there, and he's xn, they can make out xn that he has, given reply with a 40%. We want to avoid this to maintain the privacy, but also maintaining the accuracy. This is the aim. Is that formation correct?
Yes, sir. Yes.
Of the objective?
Yeah.
Okay. So now what he does, this guy does, when he releases the average, he does not release the average. So here fx was the correct average. In this fx, he adds some noise, n. Now, what is happening basically, this noise which is there, when he will release, expected value which is there, this remains the same. In the expected, this n will also come. So expected value of fx will become fx and this noise will come. So now you cannot come to know that this noise which is there, from where it has come, whether it has come from xn or it has come from x1. So due to which what has happened, your privacy has been maintained.
Yes.
Okay. This is the basic Laplacian, what we are doing. And for the error which is there, this fx plus n, the error will be there. This is f dash x, for example. Error is f dash x minus fx is equal to expected error. This will become expected of noise. Is this okay? Noise we know.
Sometimes the screen
Yes.
freezes.
Now is it okay?
Yeah, but still you have written something which is not visible.
Acha, acha.
Now visible. Now
Okay.
visible.
I'll share the notes here. Now this noise which is there, it belongs to Laplacian 0 over any. Laplacian has got a property that when you take like this, its expected value will become 1 by any. Is this okay? Nitish, is it
Yes.
okay? So now by this, what has happened? So this is your error. Now this error we want to reduce. And this is of a order of what? 1 by any. So earlier, for example, if I give you an example, that in the random response, there are some n is equal to, for example, 10,000. So your random response error would have reduced by just by 1 by 100. Whereas trusted curator will decrease by 1 by 10,000. So this is the benefit of your trusted curator. Is it okay?
Yeah. Okay.
Yeah.
Okay.
Okay. So this was trusted curator. What I will do, I will share this document with you. So I will not go through the PYQs. Most of the PYQs are there. I have explained all these concepts. I have found some extra material also. So I'll convert this into PDF. I will share with all of you. You go through this. In cases there is any doubt in any PYQ or in any GA, the questions are very, very straight. There are some questions from week 1 to 6 also on some concepts. So please go through them, and in case there is any doubt, we can discuss tomorrow. We have got time till tomorrow also. Okay. So with that, I will finish this session. It has been quite a long session. Any question, Surupi, Ravina?
No, sir. Thank you.
Yeah,
Thank you.
Ravina from your side.
No, sir, no question. Thank you, sir.
Yeah, yeah. So please keep on posting your questions. Your questions are, very, very important. It is very nice to see somebody thinking so critically and to go
See,
in
I,
deeply.
I feel like it's stupid to ask this question. Then I stop myself from asking. But then I thought, let me ask.
Ravina, never. I'll give you my piece of advice. Never think that any question is stupid. Okay, no question is stupid. Okay, and we all are learners in this journey. We all are learners. Either we will, deliberate, discuss to find the answer, or we'll make efforts to find the answers. But there is no question who's stupid. The day you start, stop. The day you stop asking questions, that day your learning stops. Okay, I can say that.
Yes, sir. I
Yeah,
agree.
yeah. Chalo, wish you all the very best. Okay, go through this document. I'll share that. Thanks for joining in. Have a nice day. And in case required, we'll connect tomorrow. Okay, bye.
Yes, sir.
Thank you.
Thank you.
Bye bye. Thanks for joining.